Okay, so I guess this is a pretty natural follow-on from Terry's talk, and Terry's probably fast asleep now, so you probably won't argue with too much of what I have to say. I also feel a bit jet-lagged as well. But I'm going to give you an overview of silicon photonics approach to quantum photonics. I'm also going to say a little bit about the kind of the background of integrating quantum photonics in general, and where this field came from, what we've achieved, and say a little bit about where the field is going. And Terry had his way of motivating the use of photons. I think looking at Di Vincenzo's criteria for quantum computing or quantum technologies is another good way of assessing the quality of your qubits and your systems for quantum computing or quantum information processing applications. And so whether you're ion trapping or superconducting or photons or myron or fermions, you have to adhere to these criteria that Di Vincenzo came up with in 1998. And if you look at how photons map onto this criteria, the first four criteria, photons map very well. You can have very well-defined qubits depending on your particular degree of freedom that you decide to encode your photons in, whether that's path, polarization, frequency. You can initialize the state of those qubits, so you can basically control the information that you impart upon those qubits very, very accurately. Then you can measure them with single photon detectors, and photons are obviously famous for having a very long or low coherence time or not having any decoherence at all. The last criteria, number 5, is that you need a universal set of quantum gates, and this is where things get a little trickier. So for quantum computing, you need an arbitrary single qubit control. You need some sort of non-trivial 2-qubit interaction. So the arbitrary single qubit control is very readily achievable in photonics using things like Mach-Zehnder interferometers, or in polarization encoding using birefringent material. But it's this last one that has always been the sticking point for photonics as an approach to quantum computing. And it was considered for a long time that photonics could never be used for quantum computing because of this lack of an ability for 2 photons to deterministically interact with each other. Now, there's been a lot of research into how you might achieve this. A lot of research, a couple of Nobel Prizes, and the way people are looking at getting photons to interact is via some sort of light-matter interface. Whether that's ion traps or quantum dots, nitrogen vacancy centers, atomic systems, there's a whole bunch of technologies or approaches that you can use via matter to get photons to interact with each other. And these technologies are progressing very, very, very rapidly. There's some really excellent research and very promising results coming from these technologies, but they're still very far from being manufacturable and scalable and having performance across all of the key metrics that you really need. And so, so it's still considered that can we really make photonic-based quantum technologies? Now, in 2001, Knilfam and Milburn came along and put forward their proposal for a linear optical quantum computing scheme. And so this was, I guess this blew everyone out of the water. This basically said almost the opposite to what everyone believed at the time. And they said, well, yeah, you can use nothing but linear optical components to get a quasi-deterministic light-matter interaction, or a quasi-deterministic photon-photon interaction. And that was done by effectively using ancilla photons, using measurement-based nonlinearities. And their initial scheme that they proposed was required huge amounts of resources, required incredible levels of performance from the components. But in principle, it showed that it was possible to do quantum computing with photons, and in principle that this system would scale. Admittedly, at the time, the size of the system required was huge. And so, bottom line is that with photon sources, with mirrors, beam splitters, phase shifters, linear optical components, and with photon detectors, it is in principle possible to do linear optic quantum computing. Now, the first sort of versions of this were based on the sort of circuit model approach to quantum computing, as have a lot of early stage quantum technologies. And as Terry very well highlighted today, photonics maps very naturally onto a cluster state approach to quantum computing. And most serious efforts in quantum computing these days are focusing on this cluster state approach. And so in that approach, we're able to generate entangled photons, we propagate those entangled photons for a period of time, and then we measure out those entangled photons. And this is the basis of the system. And pretty much in photonics, all the complexity happens at this point here where you're generating entanglement. And based on the principles of KLM, we actually generate entanglement by doing measurements. And so really the system here is measurement, propagation, and measurement. And that's the basis of the optical process of quantum computing. So I won't say much more on that. I mean, Terry covered that in pretty good detail. But what I will say a bit more on is that if the technology is required to generate the resources to do linear optical quantum computing. So you need to create entangled states, and this is probably, or was in 2012, the state of the art for generating entangled states. This is Jianwei Pan's experiment. He created an 8-photon entangled state. He recently bested that with a 10-photon entangled state. So the circuit was probably twice the size, I'm guessing. It probably took some poor student twice as long to cobble it together. But it's clear that this heroic experiment, but it's not a scalable technology in any sense. If you want to make something 10 times, 100 times, 1,000 times more complex, it's just not going to happen. And so, the vision is, can we apply state-of-the-art photonic engineering approaches and principles to this physics demonstrator to create a new type of technology platform? And so can we crunch all of that complexity down onto miniature integrated quantum photonic circuits and get all of the functionality and the performance that we need to ultimately scale up towards quantum computing applications? And so in 2008, Bristol published the first demonstrator of a quantum logic gate based on this waveguide technology. And I think the key take-home messages from that were really, it was the additional inherent stability that you got from writing circuits into blocks of glass that made this such a significant piece of technology. Because once you've got stability within your system, you can then start to think about making your systems more complex, scaling up these systems, concatenating systems, and it gives you a route to scalability. Previous approaches on these big optical benches, everyone was fighting against the instabilities of the system. The fact that it's compact, I guess, is definitely an added bonus, but it's really the stability of these systems that really gives you the advantage. And so using that glass-based approach to waveguide circuits, a whole host of demonstrators have been done across communications, computing, sensing, and simulation. And this was one of the first programmable circuits that we had at Bristol. This is a relatively simple 2-qubit circuit where we're able to control single qubit manipulation to control the state of the photons that we put into the circuit, then a control NOT gate that allows us to perform entangling operations on those photons that we inject into the circuit, and then tomography circuit at the end. And with this relatively simple 2-qubit processor, you could do really quite a lot of experiments. If I gave you a 2-bit classical processor, an AND gate, there's really not a lot you can do with that, but it's surprising how much you can do with a 2-qubit processor. So we generated Bell states, we did mixed states, even did a quantum chemistry algorithm using this chip. We took this a step further, and Jacques Caroline, we took this online, I should say. So this was, regardless of what IBM say, we did the first online quantum computer. They failed to somehow accept or acknowledge that. But back in 2013, we put that chip online, and it got a lot of hits. I think it was getting thousands of hits a month when we first put it up there, and it was still now I think it's still getting about 1,000 hits a month. That chip is now in the British Science Museum, which it sits next to an Enigma machine, which I think is really cool. So that's something that we're very proud of. So if you're ever in London, go check it out. It's a good exhibition. There's a Babbage difference engine in there as well. So anyway, we took that technology a step further, and this was work done by Jacques Caroline, who's going to be speaking next, and Anthony Lang, I think, is at the back there. And we made a completely arbitrarily reconfigurable 6-mode unitary circuit. So what this allowed you to do was 6 modes at the input, 6 modes at the output. You could program that circuit to do any possible thing you could ever do on 6-mode in and 6-mode out. And so that allowed us to perform thousands of quantum optical experiments, pretty much every experiment that had been done up until that point, and then a whole bunch more in just a matter of a couple of months. So it was a really powerful programmable platform. This was made by NTT, and this is what the circuit looked like. So this was fabricated on I think it was a 4-inch wafer, and you could fit 2 of these chips onto 1 wafer. And if you look carefully, the chip's so big that it's actually bent back around upon itself so that it would fit onto the wafer. And so we're kind of almost back to that same problem again of, you could maybe make this twice as complex, but you couldn't make this 10 times or 100 times more complex. you just run out of wafer. And so it got us scratching our heads again and thinking, how do we miniaturize this? And then of course, we were just using this to manipulate photons. So how do we start to add additional functionality? How do we actually generate states on chip? How do we detect states on chip? And then how do we move to a fully integrated platform? So over the course of a couple of years, we looked under every photonic rock, and we very much explored every photonic material system that's out there. And we might as well have not bothered, because it's pretty obvious in the end that you go to silicon. It's people time again try and do something different from silicon and end up going back to silicon. So it was no surprise that we ended up choosing silicon as the technology platform. And the reasons for that are, well, I think mostly it's that it's such a well-established technology platform. It's so readily accessible and it's so high-performing that it has a real draw to it. But I think technologically, it allowed us to go to much smaller bend radii, and what bend radii basically translates into component density. And so going from the glass waveguide circuits that have millimeters bend radius, going to the silicon circuits that have micron bend radius, you basically got a scaling factor of about 1 million in component density. So all of a sudden, you've got yourself 1 million times greater component density or complexity that you can have within your circuits. And then there are other advantages. It has a really nice high Chi3 nonlinearity, so you can use that for photon sources and generating entangled states of light. And so within silicon, you can realize all of the core technologies that you need, all those linear optical components that you need. And if you're a photonic engineer who's working in silicon for say a datacom application, and you look at this, it's no real surprise. There's nothing there that would particularly frighten an average photonic engineer, except maybe when you put single photon in front of your detectors and sources, and that maybe looks a little frightening. Okay, so the hardware requirements are quite simple. We need some way of generating photons, some way of manipulating photons, and some way of detecting photons. And so for the rest of the time, I'm going to just go through some of the approaches that we've used to do that in each of in silicon photonics. So the way that we generate our photon states is we use a process known as spontaneous four-way mixing. And so this uses the very high Chi3 nonlinearity of the silicon, and effectively we pump the material with a bright light beam, and then 2 photons within that bright pump spontaneously interact with the Chi3 nonlinearity and get scattered to a higher energy signal photon and a lower energy idler photon. And that in itself is a quantum mechanical process. Those photons are correlated, and this allows us to effectively extract single photons from the pump beam. And it's those single photons that we use within all of the experiments and demonstrators. And so you can take a silicon waveguide, just a normal silicon waveguide. It's 6 millimeters in length in this particular example, and you pump it with a pulse laser source, and then you can see that you get this quadratic increase in the pairs that get generated as you increase your pump power. You can use more novel structures to enhance the performance of the source. In this case, we use a ring resonator, and so light now gets trapped inside this ring resonator. It oscillates around the ring resonator. It gives us an increase in the intensity of light, which then increases the efficiency of the four-way mixing process, and so we can have more efficient sources, and we can also use the spectral properties of the ring to shape the spectral properties of the photons that get generated. And so using this ring, we were able to get count rates up into the sort of hundreds of megahertz, with approximately 100 times improvement in efficiency over standard straight waveguides. You can tailor the spectral properties using these rings, so you can make spectrally disentangled photons. So it's very important to have spectrally pure photons when you want to do multiphoton experiments. And so we were able to get very nice spectral properties from these photons. And in using those photons, we were able to, you spectrally shape those photons. You can now think about doing experiments where you're interfering photons from multiple sources. So if you want to scale up your technology, you need to be able to make sources that are identical to each other and sources that produce spectrally disentangled photons with high purity. And so within this experiment, we had 2 sources that you can see here and here that were very, very close in performance to each other. So the spectrum is very, very similar. We then used a filter to separate our signal and idler photons, so we could herald emission of photons from each of those sources, and then we could then interfere those sources upon this Mach-Zehnder interferometer here, and effectively do a Honger-Mandel interference experiment between these 2 heralded sources. And so what we observe is these on-demand interference fringes, and you can see that you get this difference between the red, which is the classical or indistinguishable case, and the blue, which is the indistinguishable case. And what we were able to see was that we could get visibilities of around sort of 72%. The actual calculations that we had the purity of our ring limited to 92%. That's due to intrinsic properties of the particular structure of the ring. And this matched very nicely. And what we found is that the reduction in purity was mostly due to effects of multiphoton contamination. That was just because the experiment, we had to pump it quite high. But if we reduce the pump rate, we would expect the purity to go, in this case, to the limit of 92%. And that limit, you can increase the limit of that purity by engineering your photon source. And so by controlling the spectral properties of your pump and your signal idler, you can push the purity of your photon source up to near unity by moving to these sorts of structures. And so in the next work that we do with this, we hope to be able to push the purity much, much higher towards the levels that you might need to do, the sort of metrics that Terry was talking about earlier. You can further improve the efficiency of the sources by using higher Q cavities, moving to things like photonic crystals. And so in this work, we use a photonic crystal cavity that allows us, so the per generation rate scales with the Q of the cavity to the power 3. So the higher the Q, the higher the per generation rate that you can get. And with a single photonic crystal cavity, you have just one resonance. And so to get around that problem, we coupled 3 photonic crystal cavities together to break the degeneracy of the system. We got these 3 supermodes within the cavity. And then we were able to get a per generation rate which was about 100 times more efficient than the ring resonator source earlier. So a whole bunch of photonic engineering techniques that you can use to spectrally shape these photons to improve the efficiency of these photon pair sources. And there's a whole bunch of other things that can be done, will be done to further improve the performance of these sources. Okay, so now you've generated your photons, you have to manipulate those photons. And how well you can manipulate your photons kind of translates into effective Pauli errors within your system. And so you have a photon at your input state here, and you want to translate that into another state at the output. And if you think about this in terms of Mach-Zehnder interferometers, then you can directly translate the error into an extinction ratio of your Mach-Zehnder interferometer. And so we configured this simple circuit to sort of test the limits of the performance of these integrated Mach-Zehnder interferometers. And what you find that with fabrication tolerances of your beam splitters, that limits the amount of extinction ratio that you can get. So the extinction ratio is basically if you input a photon here and you're trying to configure the circuit so that your photon comes out of this port here, how many additional photons will come out of this lower port? What's the probability that your photon will go into the wrong port? And so in this case, with about a 1% fabrication tolerance, it's about 1,000 to 1. But really, we want to be much more in the kind of million to 1 in terms of the level of control that we can get. And so what we did is we took this circuit and we took each of these Mach-Zehnders and we replaced them with configurable elements. And so now what we could do is tune these beam splitters to be exactly 50-50 and tweak and tune them and completely balance the Mach-Zehnder interferometer. And in doing so, we were able to go from a kind of intrinsic 30 dB extinction ratio to this tuned sort of greater than 60 dB extinction ratio. And in this case, we think we're limited not by the precision of the control, but more to do with scattering of light within the system. And so you can get these very, very, very high levels of precision of control over your single photon states. Another important aspect is pump projection. So we use a bright pump beam to pump our photon sources, but then we're generating just a couple of photons. So you're putting billions of photons into this system, trillions of photons even, and then you just want to try and pick out 2 photons. And so you need incredible levels of pump projection within the system. And if you go through the calculations, it turns out you need somewhere between 120 and 140 dB of pump projection within your system, which is very large. The way we looked at doing that is the importance of these pumps are really, at some point you want to integrate your detector within your system. And so what you can't have is some of the pump from the photon, some of the photons from the pump going into your detector and giving you false events. And so the way that we looked at doing this was to use something called an asymmetric Mach-Zehnder filter, and then cascading lots of those filters together to get the level of suppression that we needed. And so in this experiment, that's exactly what we did. And you can see as we go from a 2-stage of cascade to a 4-stage of cascade, we're indeed getting higher and higher levels of suppression. And at some point, we hit this noise floor. And it turned out that this noise floor was due to scattering within the system. As you can see from this figure here. So we could get around that scattering by moving to a multi-chip solution. And the next step of this is to do scatter mitigation on the chip by doing deep X trenches, these sorts of things. Okay. And by cascading those two chips together, we could indeed get the levels of suppression that we needed and observe single photons without needing to use off-chip filtering. All right, just a quick word about delay lines. Delay lines on chip are actually much better than most people realize. If you go to very wide waveguides in silicon, you can get down to a couple of dB per meter. So you can get sort of sub dB per nanosecond delay on a silicon chip. If you go to glass waveguide circuits, you can even get down to the sort of the almost milli dB per nanosecond delays. So delays on chip are actually much better than people think. If you think about switching, you can use a lot of the switches that you get from the telecom industry, these carrier-based switches where you can get up to gigahertz speeds. Losses are potential issues with those switches, but there are new switching technologies coming out using the intrinsic using a Chi2 induced nonlinearity within silicon. This is some nice work out of MIT where they were able to induce an effective Chi2 nonlinearity within silicon to get very, very fast, low-loss switching. And then this is an example of switches operating at cryogenic temperatures to show that you can overcome some of the issues of cooling these systems down and still have your switches operating at cryogenic temperatures. Single photon detectors. A lot of work being done in single photon detectors integrated onto waveguides. And here are just some examples of some of the really high levels of performance you can get. You know, people are getting up to 96% efficiency on chip single photon detectors. And so you can take all of those components and you can then integrate those components together to create all the sort of subsystems that you might need to do linear optical quantum computing. And I won't say much about those subsystems, but they're effectively combinations of direction couplers and beam splitters and detectors and photon sources. How do we then start to integrate all those together? I'm going to very quickly run through a bunch of examples of circuits that we've integrated together to show how we can increase the complexity of these technologies. So this was the first example where we integrated 2 photon sources together and showed that those 2 photon sources could get very, very high levels of quantum interference on a chip. We then went a bit further and had 2 photon sources integrated with ring resonators, integrated with tomography circuits that allowed us to do qubit generation of Bell states and investigate the spectral purity of those photons. We then integrated 4 photon sources to do a 2-qubit logic gate, integrated with a programmable logic gate here. This is a programmable CNOT gate. And then that allowed us to generate entangled states, disentangle entangled states, and do a whole bunch of investigations on generating entangled states. This is a universal 2-qubit processor where we've got 4 sources integrated with a very large reconfigurable circuit that allowed us to implement all sorts of different types of logic gates. And so you can imagine with scaling these sorts of systems that you can get incredible levels of complexity on a single chip. And then maybe one way of scaling up is to actually have photonic interconnect between submodules. And so this is an example of how you might realize such a photonic interconnect. In this chip, we generated entanglement on one chip. We went from path encoding to polarization encoding and distributed half of that entangled state onto another chip, and then showed that we could violate a Bell's inequality between the 2 chips. So a rudimentary example of how you might start to go about doing a distributed quantum system. In terms of scaling up, this is one of our most recent demonstrators where we did a 16-dimensional entangled state generation, so very high dimensional entangled state generation, using a circuit that comprised 16 photon sources, all identical, with filters to separate the signal and idler states, with a total of about 600 optical components on a single circuit. And so, as you can see, we're increasing the complexity of these circuits really quite dramatically. And over the last couple of years, we've really tracked very nicely this kind of Moore's law scaling in quantum photonic components. So anytime soon now we'll be coming out with 1,000, and in a year's time we'll be 10,000. So, looking at my students at the back there, get working, guys. And where can it go? In classical photonics, people are already up at 10,000 plus components in a single circuit in classical photonics. People like TSMC and Global Foundries are teamed up with photonic companies creating circuits using state-of-the-art manufacturing processes. And so you can now go out and you can buy a 300mm wafer that has over 1 million photonic components on that wafer coming out of state-of-the-art fabs. You can even co-integrate electronics and photonics within these systems. There's an example with 70 million transistors and 1,000 photonic components used within a classical computing application. And so, what might your end goal look like? This is, your quantum computer may end up looking something like this, which is an image out of a classical supercomputing article showing how photonics may be used in future supercomputers, where you have photonic layers connected together being supported by an electronic orchestration layer. And I don't think a photonic-based quantum computer will look too much different from this, maybe except you maybe need to cool it to cryogenic temperatures. And so, what might our end system look like? You can imagine millions of photonic components onto wafers cooled to cryogenic temperatures to support the superconducting detectors, and then connected together into a data center style architecture. I just want to in the last minute, just kind of give a small industrial perspective on this, because wearing my other hat, I get a kind of a view into what's happening in the industry around this. And it really kind of opens your eyes to what's possible. And in some sense, it makes you realize that the impossible is much closer than you think when you start to see what is done and what can be done in the industry. Just an example of that is if you just look at advanced CMOS manufacturing, it blows your mind. If you look at the state-of-the-art 3D NAND architectures, this structure has 30 to 60 layers, all nanometer thick films grown on 300mm wafers in a mass manufactured high yield environment. And it's just amazing that they can do that. And if you look at the latest transistors that are coming out, they're down at 7nm feature sizes. If you look at the latest microprocessors, 7.2 billion transistors. And if you look at some of the world's most powerful supercomputers, thousands of core processors leading to trillions, hundreds of trillions of transistors. So when you look at what other people are achieving in the computation space, it really blows your mind. And quantum computers at least need to be somewhere towards this level of complexity to be able to really genuinely cope or compete with classical computers. And so what does this mean for photonics? If you look at people who are now using these very, very high-end processors for photonic technologies, they're able to get incredible performance where across a whole 300mm wafer, they're fabricating waveguides that fluctuate in dimensions by sub-nanometer features across the whole of the wafer. The resonance shifts are incredibly small on these resonance-based structures. If you look at the kind of line edge roughness that they can achieve on these waveguides, they're now getting propagation losses that are approaching 4 times better than you would get from sort of the older school foundries. And so, and that's without much effort in sort of developing these processes and techniques. So I think the message is that there's a lot of overhead left in silicon photonics by applying really advanced manufacturing processes. So my conclusion really is basically that silicon photonics and advanced CMOS manufacturing can be used to realize complex quantum photonic circuits, and it's a really viable route to achieving a large-scale universal quantum computer. All right, sorry for overrunning.
No, good, thank you.
I'd like to thank these guys for all of their hard work.
We have time for one quick question. Dr. Clark.
Very nice talk, Mark. Glad to hear that it's moving forwards. With regards to integrating electronics with the photonics, as I understand it, you need a different type of wafer when you move to these electronic systems. So are you going to move all the photonics to these thinner wafers, or move the electronics the other way? And how close do you need the electronics to really be to the photonics?
Yeah, I mean, it's a nice option to be able to have the electronics there. I think realistically, I think it's a big compromise. You're compromising on your photonic performance and your electronic performance to integrate them together. And I think probably the best strategy is go with the most optimized photonic process, go with the most optimized electronic process, and then do some kind of flip chip bonding. I think that's realistically the right way to go.
Okay, thanks.
Cool. Let's thank Mark again. In our next talk, it's again a pleasure to welcome back Jack Carroll.